All right, hello. Welcome to our final week of Math 2413 weekly reviews. So this week we're going to be covering indefinite integrals, the substitution rule, and we're going to touch a little bit on area under curves. So let's go ahead and get started. So first thing we're going to cover today is going to be indefinite integrals. So let's go ahead and get started with this. So our fundamental theorem of calculus states that derivatives and integrals are inverse functions. We also know that antiderivatives are also an inverse of derivatives, like that's the exact opposite process. So therefore, what we can do is we can treat integral notation to represent antiderivatives. So by that, what we mean is like we can say that the integral of small f of x dx equals that large f. That also means that if we take the derivative of that large f, we get back to the small f. So what we can think of this is like we have our integral notation, and then we have like our antiderivative notation. But these essentially mean the same, but these mean the same thing. So now let's go ahead and get into indefinite integrals. So our indefinite integral is actually going to be exactly this format that we have right here. So there's some key things to note when we're looking at indefinite integrals, so as opposed to definite. So our indefinite, those are going to be unbounded. Yeah, those are typically going to be unbounded. So you see right here and right here, whereas in a definite integral, we had something listed right there. That doesn't really have anything. So, and in contrast, our definite integrals are typically bounded. But the more important criteria is going to be that an indefinite integral will produce a function. So it would be that large f of x right there. This is going to be a function of something. Whereas a definite integral, that's going to produce just a plain, that's going to produce a number. Like just like a constant number, like 2 or 23 or 44 or something like that. So now that we kind of have that, let's go ahead and I'm just going to do a quick little thing, just kind of to show you, like to define and just say whether or not they are definite or indefinite. Just a couple quick little examples. So for part A, we're going to have our integral of 3x squared plus 1 over x dx. For B, we're going to have an integral from A to B of f of x dx equals 24. And lastly, for C, we're going to have an integral of g of x dx equals 72x to the 2/3 plus c. So let's go ahead and look at these criteria real quick. So for our first part, we can see, of course, that these do not have bounds. So therefore, we can assume that we can't really do anything to solve for a number. So therefore, this one is going to be indefinite. For part B, first of all, we can see that we have bounds. And second of all, we can see that it produced a plain number, even if we don't know what that function is. So therefore, we can say that this is an example of a definite integral. And lastly, for C, once again, we can see we have no bounds right here. And this has also produced a function right here. 72, we have a function of x, not just a plain constant number. So therefore, this is indefinite. Now, if we go ahead and take a look at our indefinite integral, there's actually something interesting that we have right here. Right here, we have this little plus c. So when we solve for indefinite integrals, you're always going to have to include a plus c. Because if we go back to our derivative rules, we know that the derivative of a constant is going to be 0. But let's say we're trying to take the antiderivative or integrate a function. How do we know that there wasn't a constant there? We don't, because so what we do is we mark a little plus c to indicate, hey, there's probably some constant right here, and it just kind of marks that because for example, like if we took the derivative of x squared plus 1, x squared plus 3, x squared plus 42, they're all going to give us 2x. But if we wanted to integrate that 2x, then we don't know. We know that 2x is going to go to x squared, but we don't know which one of these this goes to. If it's any, it can go to any constant. So what we have to do is we have to write that plus c. So now let's go ahead and get into how to actually evaluate our integrals. So as I said earlier, evaluating an integral is essentially taking the antiderivative. So I know within your textbook there is actually a really nice table with a lot of different strategies of things that you can just kind of plug and chug to get. And with a couple little rules. So you have like your constant multiplier, you can break them up by adding and subtracting, and there's also just a bunch of ones like your trig rules, your natural log rules, things like that. So let's go ahead and do a few examples to kind of integrate using some of these rules. So our first example is we're going to evaluate the integral, and then we're looking at just indefinite integrals for right now. And this is going to be 5 plus 2/3 x squared plus 3/4 x cubed dx. So now let's go ahead and look at this when we take our antiderivative. So we can see that all of these are just simple powers. So what we can do is we can kind of use our normal power, like we can kind of do the reverse of our power rule. So our first part that we're going to have is we're going to have our 5x, it's going to be our 5. So we have a 5 and we can treat that times x to the 0. So if we take the antiderivative, that's just going to get us 5x. Now our 2/3 x squared. So I usually like to pay attention first to your exponent. So we know we're going to have to add 1. So that's going to be x cubed. And now we kind of have to think about what how are we going to get this 2/3, like if we kind of reverse engineer back to a derivative. So we know there's nothing that we can really do about that too. But if we derive this and we bring this 3 down, what do we have to get that 2/3? Well, we're going to have a 9 because that 9 and that 3 are going to cancel out. And we can see this in a second when we go ahead and try and derive this to double check our answer. In a similar way, we can see that this piece right here, we have our x, and it was originally to the 3rd, but now we're going to raise that up to the 4th. And now we think about what's going to give what's 4 times some number n is going to give us 4 times some number n is going to give us 3/4. Well, divide by 4, and we can see that we're going to get 3/16 right there. And then, of course, we have to add our plus c. So now what we can do real quick is just derive this to double check and see if we're on the right track. So if we take the derivative of this function, if we take the derivative of 5x, that's just going to go down to a 5. If we take the derivative of this 2/9 x to the cubed, you're going to bring that 3 down. So 3 times 2/9 is going to cancel out to 2/3. And then we subtract 1 from that 3. Then we have this 3/16. So we do 4 times 3/16 is 3/4 times x to the 4 minus 1, which is 3. And we know that's just a generic constant c, and the derivative of any constant is just 0. So we can see that we get the same thing when we derive our integral as we did when we started. So now let's try some more examples. So in this one, we are going to integrate the square root of t times t squared plus 3t plus 2 dt. So let's go ahead and look and see what we can do with this so far. So we kind of have two functions multiplied together. But since these are all just normal power functions, what we can actually do is we can distribute. We can go ahead and distribute this square root of t to all of our other terms. And we can go ahead and treat this as t to the 1/2. So then we can then have t to the 1/2 times t to the 2 is going to be t to the 2.5 or 5/2 plus our 3, and we have t to the 1st plus t to the 1/2, which is going to go ahead and get us t to the 3/2 plus our 2t to the 1/2 dt. All right, now we're in a better spot to where we can go ahead and integrate this function. So of course we can start just by doing our reverse power rule right here. So we can get t, we know 5/2 plus 1 is going to be 7/2. And what we can do is we can go ahead and divide and multiply times 2/7, since that's going to be that inverse of what we had. Then we can have our t to the 5/2 when we add our 1 back to our exponent, and then we can go ahead and we're going to have our inverse of that exponent is going to be 2/5, but we still have that 3, so we're going to be left with 6/5 right here. And then lastly, we know t to that 1/2 is going to go to 3/2, and then we're going to do 2/3 times 2, which we have out in front, which is going to get us to 4/3. And of course we have to add our plus c to get us there. And usually I find this easier to work out with fractions rather than decimals or anything like that, just because this makes it easier to kind of think about, oh, we just kind of multiply times the inverse of that fraction. Let's do one more indefinite integral, and then we'll move on to trying a definite example. So for this one, we're going to integrate x squared plus 1 plus 1 over x squared plus 1 dx. So now let's kind of look at what we have right here. So let's go and look at this piece by piece. If we're trying to integrate this x squared, then that's just going to be a simple power rule. So we're going to have x cubed, and that inverse of that 3 is going to be 1/3. If we integrate that constant, if we integrate any constant, then that's just going to be that constant times x. So if we integrate 1, that'll get us 1x, which is just x. And lastly, we have this little fun piece right here. So this piece, if we think about all of our formulas that we've kind of worked with so far, we can see that this one, it looks like it's in the form of an inverse trig function. And if we go ahead and we take a look at our chart, we can actually see that the integral of 1 over x squared plus 1 dx is in fact equal to arctan of x plus c. So we're just going to have arctan of x. And of course, we need to add our plus c to the rest of the function. All right, so now let's try a quick example with a definite integral. Because last week we worked with definite integrals, but there was a lot, because we had the Riemann sums of trying to do definite integrals, and then we had geometric. And now this is just going to try again with just doing general antiderivatives / integrals. So for this example, we are wanting to integrate from 0 to 2 pi, pi over 2, of sine of 2x over sine of x dx. All right, so if we take a look at this, we have a sine of 2x over sine of x, and now we can't just simplify that to be like a sine of 2 or something, right? So what we actually need to do first is we need to go ahead and use trig identities to go ahead and see if we can fix this to make it something a little easier to integrate. So if we actually go ahead and look at our double angle identities, we can actually turn this into our integral from pi over 2 of 2 sine of x cosine of x over sine of x, and of course our dx. And now we can actually play with this. So first of all, we can see that we can go ahead and cancel out this sine of x right here. So then we are left with our integral from 0 to pi over 2 of 2 cosine of x dx. So what we're going to do here is we're actually going to go ahead and take our indefinite integral first. So if we just do our indefinite integral of 2 cosine of x, that 2 is just a constant multiplier, and if we integrate cosine of x, we're going to be left with sine of x. And then our plus c. Then what we do is we can go ahead and play with our bounds and go from 0 to pi over 2. So actually when we're doing definite integrals, we actually don't really have to worry about this plus c that much, because it's going to cancel out at the end anyway. But if you're doing an indefinite integral, you have to keep that. But if we're doing, once again, if we're doing definite, it's going to cancel out anyway whenever whenever we do our bounds. So what we're going to do is we're going to go ahead and plug in our upper bound. So it's going to be 2 sine of pi over 2. And really, we can go ahead and write that plus c just to show. Minus, and then we're going to subtract that with our lower bound plugged in. So 2 sine of 0 plus c. So if we look at this, we can see that those c's are going to cancel out, which is why we say we don't really bother with it. And now if we put it in, we're going to get 2 times 1, since that's sine of pi over 2, and then we're going to get 2 times sine of 0, which is 0. So that's getting us 2 minus 0, which equals 2. So now let's go ahead and get into some basic applications. So whenever we looked at fundamental theorem of calculus last week, part 2, our fundamental theorem of calculus part 2 stated that if we have our integral from a to b of f of x dx, that equaled to our antiderivative of b minus our antiderivative of a. Well, if we think about that, then really we have, because as we said earlier, we know that we can let, since we know that the small f is the derivative of our big F, we can say that large f prime of x equals small f of x. So yeah, we can then plug this into, say, large f prime of x dx. So this brings up something interesting. So we can kind of treat this, if we just look at these two pieces, we have an f and we have an f prime. So when we talked about derivatives in the semester, we always say that those are going to be a rate of change. So this is going to be the rate of change is what this represents. If we have our f prime, that's a rate. But then if we go ahead and bring that out, if we go ahead and bring that up to just a plain f, we can see that this is actually going to just be just a general change in y. Which brings us to the idea of our net change theorem. So our net change theorem states that the integral of a rate of change is the net change. And it is based on what we just looked at up here. So this is kind of like, so we have our net change. So what this is showing is like we have, like that's what our total difference is whenever we account for everything. And net is actually going to be kind of important, and we'll kind of go over like what we mean by net whenever we do an example in just a second. So some examples of this are like we can use volume or volume problems. So for example, for volume, we can let v prime of t equal our flow rate. So if we integrate that flow rate to find for our regular v of t, then that just means v of t is going to be our change in volume. Or really, by that we mean like vt2 minus vt1. And we can kind of look at the same thing with velocity as well. So for example, if we have a position, we can let a position function equal s of t. And we know that if we take our derivative of our position function, that is actually equal to our velocity function. So therefore, if we integrate our velocity function, then that is going to be equal to s of t2 minus s of t1. And that is equal to the displacement. Now, displacement is kind of saying how far away from point A did you move. So if this is your starting point, and this is your end point, it doesn't matter what way, like how you got there. This is going to be your displacement. It doesn't matter if you traveled in a straight line like that, or if you kind of just curved around, or if you did something like this. It doesn't matter how far you actually traveled. It doesn't matter how much how long you took to get there. It's just what's that distance from point A to B. And this is what we mean by net change. So if we have, it's easiest to explain net change actually in terms of a velocity graph. So if we have our graph, and our x-axis is time and our y-axis is our velocity, we can see that these are actually broken up into separate pieces. We have this piece which we can call A1. We have this piece which we can call A2. And then we have this piece which we can call A3. So what we mean here is that, and with this we mean that these are like absolute values for area. Like how much space is in there, not necessarily like is it above or below. So if we have displacement, that is whenever we have A1 minus A2 plus A3. Because if we think about displacement is related to the net, because for example, like we gained some here and then we lost some here and then we gained more here. So ultimately we kind of have an overall gain that doesn't really paint the full picture. Whereas distance, on the other hand, takes into account everything. Distance is kind of equivalent to that A1 plus A2 plus A3. Because distance is like, okay, because distance is showing how we had, like, okay, we went here, and then we had some more here, and then we went here. It doesn't really take into account direction or anything like that. It's just how much is there. So now let's go ahead and try to work on an example with this. So for this example, So for this example, what we're going to do is we're going to use the given acceleration function and the initial velocity to find the velocity function and the distance, or well, the velocity function, distance traveled, and total displacement. So, and in this piece, we are going to use the acceleration function a of t equals 2t plus 3, and our initial velocity is going to be -4. And we're also going to be looking when t is in between 0 and 3. All right, so we can say that our velocity, so earlier we said that our velocity was equal to the derivative of our position. Well, this is kind of the same thing. Our acceleration is actually equal to the derivative of our velocity. So if we go ahead, so that means if we integrate a of t, then that's going to get us our velocity function. So our first step is going to be to go ahead and integrate a of t. So if we integrate 2t plus 3, and we don't really need to worry about bounds for right now until we get to displacement and distance. dt. If we do this, these are just simple power rules, so that's going to get us t squared plus 3t plus c. And we also know that our v of 0 is equal to 4, so we can say that 4 is equal to 0 squared plus 3 times 0 plus c. Therefore, c is equal to -4. So therefore, our v of t is equal to t squared plus 3t minus 4. So there we go, we have our velocity function. So now we have to look at our distance traveled. So our distance traveled and our displacement. So actually, let's go ahead and solve for displacement first. So as we said earlier, if we integrate our velocity function, we are going to get a position function, and if we do it with bounds from like t1 to t2, we can get our total change. So s of t1 or s of t2 minus s of t1, and that's going to get us our displacement if we just plug in our bounds as is. So let's go ahead and integrate our function. So we have from 0 to 3. So if we integrate this, t squared is going to go, t squared is going to go to 1/3 t cubed. 3t is going to go to 3/2 t squared. That -4 is going to go to -4t. And then we have our plus c. However, we're going to go ahead and take our definite integral from 0 to 3. So if we plug that in, we're going to get 1 times 3, 1/3 times 3 cubed plus 3/2 times t squared times 3 squared minus 4 times 3 plus c minus all that times 0, which all that's just going to go to 0 for everything anyway. So we can really just stop here, just because everything's going to 0. So if we plug this in, we can get, so that's going to get 3 cubed is 27 over 3, which is going to be 9, plus 3 squared times 3 over 2 is going to be 27 over 2, plus, or well, minus 4 times 3, which is 12. So we're going to get 27 over 2 minus 3, which is equal to 21 over 2. So that is going to be our displacement. Now we have to think about what our distance is. So I'm actually going to go ahead and erase some of this. Let me go ahead and just make sure I have my work copied down. There we go. So now we're going to look at our distance. So once again, we had our S of t was equal to 1/3 t cubed plus 3/2 t squared minus 4t plus c. And also our velocity function was equal to t squared plus 3t minus 4. So it's so we kind of need to pay attention to this. So if we actually think about what the graph of our velocity function looks like, we get a graph that looks something like this. So our displacement is showing, so if we're going from 0 to 3, from here to here, we're getting this volume, this area minus this area. Whereas what we want to find for our distance is going to be those two areas added together. So in order to do that, what we have to do is we actually have to go ahead and split this up into multiple integrals. So if we go ahead and factor this out, we can see that this is equal to t plus 4 and t minus 1. So therefore, at t equals 1 is going to be where we're going to have to split it. So what we can do first is, we can solve for the integral from 0 to 1. I'm going to switch colors to make this less confusing. From 0 to 1 of our velocity function. So at t squared plus 3t minus 4. And if we go ahead and go back to our s of t, just plug our bounds in. So we're going to get 1/3 t cubed plus 3/2 t squared minus 4t plus c. However, we can actually just kind of ignore the plus c from 0 to 1. So if we plug everything in, we're going to get 1/3 times 1 cubed, which is 1/3, plus 3/2 times 1 squared, which is 3/2. Minus 4 times 1, which is 4. So if we go ahead and add this all together, if we go ahead and give ourselves a common denominator of 6, we're going to get 2/6 plus 9/6 minus 24 over 6, which gets us negative 13 over 6. But remember, we need to go ahead and take the absolute value to get us really what this area is down here. So we take the absolute value to get us 13 over 6. Then we go ahead and look for this area right here from 1 to 3. So we go 1 to 3. And then we already know that function. So then it's just a matter of plugging it into our s of t from 1 to 3. So we already saw it at 3 last time was going to be, so we already saw that s of 3 was equal to 21 over halves from our last example, 21 over 2. We also see from earlier that our s of 1 is going to be negative 13/6. So we're going to have minus a 13 over 6 minus negative 13 over 6, then we add together. If we do a common denominator of 6, we're going to get 63 plus 13 all over 6, which is 76 over 6, 38 over 3. And then we can go ahead and add these together to get us 38 over 3 plus 13 over 6, which we can go back to 76 over 6 plus 13 over 6, which gets us finally to 89 over 6 is our total distance. So we can see how like displacement didn't really tell us the whole story. Distance kind of shows how far we actually travel, whereas distance is just kind of that net overall change. So now let's go ahead and move into our substitution rule. So let's say we have an integral that looks something like this. We can't really integrate that using any of those previous rules that we had, since it's not really a pure power rule. There's not really anything we can kind of plug in. It's kind of wonky. So but we can kind of think about back to whenever we did chain rule earlier in the semester. So when we did chain rule, what we did was we introduced a variable u, and that let us go ahead and derive composite functions. Because we couldn't derive those beforehand, but once we introduced u, we could then plug that into our other rules. This same idea can actually be applied to integration. So our substitution rule, or what we can also call or what we can also just refer to as u sub, states that if we let u equal g of x, and that is a differentiable function, whose range is an interval I, and our function f is continuous on our interval I, then we can say that our integral of f of g of x times our g prime of x dx is equal to the integral of f of u du. So let's kind of go ahead and see what this really means. This is kind of using, like we said, this is kind of integrating a chain rule. So we have a composite function, and we have the derivative of that inner function. If we have something like that multiplied together, we can go ahead and apply our u sub rule to kind of counteract that chain rule. So what we can do is let's actually go ahead and integrate that function I gave you earlier. So we have our integral of 2x times e to the x squared dx. So what we need to do is we need to find a u, that way we can solve for our du as well. So when we look for our u, what we need to do is actually go ahead and kind of look to see, do we have a composite function and like an inner and an outer function. And then we also need to see, do we have the derivative of that inner function multiplied somewhere? So if we look in here, we have this e to the x squared, which can be a composite function. Then we can look closer and see we have our x squared is our inner, and our e to the x, and then our e is our outer. Then we can look to see if we take our derivative of x squared, we get 2x, and see is that anywhere in the function. And in fact, it is. So therefore, we can now say that our u is equal to x squared, and then our du is equal to 2x dx, because that shows that, because this is sort of like a differential, so where we can just kind of say, okay, to where we just have to say, hey, be derived with respect to x. So now it's a matter of just plugging everything in. So what we can do now is that we had that outer function e, which has now been replaced to u. And then we also have our 2x dx multiplied, so we can say just du. And integrate that, that's going to get us e to the u plus c. And then our final step is going to be just plug in what our original u was. So we can get e to the x squared plus c as our final answer. Now let's go ahead and do another one. So in this one, we want to integrate secant squared of theta times tangent cubed of theta d theta. So let's go ahead and look and see what we have. So we have our secant squared and our tangent cubed. Well, we can kind of also rewrite this tangent cubed as being tangent of theta all cubed. That gives us an inner and a composite function now, an inner and an outer. Our outer is going to be that like x cubed. And we have our inner function as being this tangent, is tangent of theta. So now we can need to look and see if we have a secant squared of theta anywhere, which we do. So therefore we can say that our u is equal to tangent of theta, and our du is equal to secant squared of theta d theta. So now it's just a matter of plugging this in. So we know we have our tangent of theta cubed, which gets us u cubed. Our secant squared of theta d theta is there, which is now just du. Once again, this is just a simple power rule, which gets us to 1/4 u to the 4th plus c. Then we just plug in our u to get us 1/4 tangent to the 4th of theta plus c, and that is our final answer. Now, sometimes we may have examples to where it isn't necessarily 100% fixed. And in that case, we have to kind of use some algebra to go ahead and play with our functions a little bit to kind of like make it work. Now, sometimes it'll be so far off to where you can't do anything with it, but we don't really have to worry about that. We don't have to worry about that for another couple months in 2414. But yeah, let's just go ahead and see how we can kind of play with this. So usually it's going to be some sort of constant multiplier is usually going to be what you're going to mess with. You may have some other instances so where you kind of have to play around with like your u and like your x and stuff. But I'll show you an example of both of those. So first, let's do a couple of examples of how we mess with our constant multipliers. So in this one, we're going to have our cosine of 1 plus 5t dt. So first, let's go ahead and look in here. We have an inner function, and we have an outer function. So let's go ahead and actually play with this a little bit and see. So we have our inner function, and we let u equal 1 plus 5t. Our du would have to be 5 dt. So we have our u, which is great. We have our outer function, which is great. Now we have our dt, but we're missing our 5. So what we can actually do is play with this section a bit, and we can actually divide both sides by 5 in this equation. So divide by 5, divide by 5. So we can say that du over 5 is equal to dt. So we have our dt, which is 5. So now we're in a good spot. So now what we do is we can actually go ahead and plug this in. So where we can say we have cosine of u times du over 5 to replace that dt. Now to make it a little easier, I like to go ahead and just pull out any constants out in front to get us 1/5 times cosine times integral of cosine of u du. So if we integrate cosine of u, that is going to get us sine of u. And we have our 1/5 out in front, and then we have r plus c. So then we just have to plug our u back in to get us 1/5 sine of 1 plus 5t plus c. Okay, so now I'm going to kind of do ones where you kind of have to... Actually, let's do one more like that. So for this example, we are going to have our integral of y squared times 4 minus y cubed to the 2/3 dy. All right, so now let's look and see what we have in here. We have a composite function, we have our inner, and we have our outer. So if we let our inner function be equal to 4 minus y cubed, then if we take our du, we're going to get negative 3y squared dy. So if we look in here, we have a dy and a y squared, and we have a dy and a y squared. So what we have to do to kind of get this back to our form is we're going to divide both sides by negative 3 to get us du over negative 3 is equal to y squared dy. So now what we can do now is plug everything in to where we can get our integral of u to the 2/3 times du over negative 3. Turn that, go ahead and pull out that negative 1/3 to get us negative 1/3 integral of u to the 2/3 du. Once again, this is just a normal power rule. So we're going to get u to the 5/3, and we're going to have -1/3 times 3/5, since that's our inverse of our exponent, plus c. Then we're going to go and cancel out these 3's to get us -1/5 u to the 5/3 plus c. And we just plug in our u, so -1/5 times 4 minus y cubed to the 5/3 plus c. And we are done. All right. So now let's go ahead and kind of play a little bit with another one that's kind of similar but a little different. In this one, we want to integrate x over x minus 1 dx. So this one's a little different. So we have a function on top and a function on the bottom. So when we do this, so if we have something kind of situated like this, a good idea is to try to see, maybe try to manipulate this to maybe see if we can use our natural log rule, since that's usually a function on top and a function on the bottom. So let's go ahead and try to let u equal x minus 1, and therefore our du is equal to our dx. So when we have this, we have our dx taken care of, we have our x minus 1 taken care of. The issue is that we still have this x up here that needs to be taken care of as well, because we're trying to get everything in terms of u. But if we look back over here in our u function, we can isolate x by itself, because we can just add 1 to both sides. And we can then say that x is equal to u plus 1. So now what we can do is we can go ahead and plug these in to our initial equation. So where we can go ahead and get our u du and then our u plus 1 up top. So now from here, what we can do is that, since this still isn't a great form to integrate, we can actually go ahead and split this into 2 separate fractions, since we have a plus sign in the numerator. So we can let this equal to u over u plus 1 over u du. That u over u is going to cancel out to just 1 plus 1 over u du. So now what we can do is we can go ahead and split this up. So now what we can do is we can go ahead and integrate this pretty easily now. If we integrate 1, that's just going to get us back to u. And if we integrate 1 over u, that's going to get us the natural log of the absolute value of u, and then plus c. So now all we have to do is just plug in our u back into our function to get us back to, so we're going to plug in our u to get us x minus 1 plus natural log ln of x minus 1 plus c. And because we have our minus 1 as a constant and we have a constant right here, we can actually kind of push this aside into our constant right there and simplify this down to x plus natural log of the absolute value of x minus 1 plus c. So now I'm going to go ahead and touch on some definite integrals with substitution as well. So for our sub rule with definite integrals states that if g prime is continuous on an interval from a to b, and f is continuous on the range of u equals g of x, then we can say that the integral from a to b of f of g of x times g prime of x dx is equal to g of a g of b times f of u du. So what this means is that we have to kind of go ahead and convert our function if we're going to do that. If whenever we have definite integrals, like you can also integrate, take the indefinite integral, and then get it in terms of u, and then turn that back into terms of x and plug in your original bounds in. Or you can go ahead and convert your bounds in terms of u as well, and then that way you don't have to go back to x. That way it's just kind of one less step. So let's do an example with this. So an example that we have says we're going to integrate from 0 to 13 of dx over the cube root of 1 plus 2x squared. So if we look at this, we have an inner function, this 1 plus 2x, and an outer function, which is that x to the 2/3. So what we can do is we can then let u equal 1 plus 2x, and then of course our du is 2 dx, divide by 2 since we don't have a 2 out there, to get us du over 2 is equal to dx. But now there's one thing that we kind of have to take into account is our bounds now. So what I like to kind of write this out is say that we have like u of 0 and u of 13. And then we have u of 0, so we just plug in 0 for u to where we get 1 plus 2 times 0, which is equal to 1. U of 13 is 1 plus 2 times 13, which is 27. So now we can go ahead and reset up our integral. So we can integrate this time from 1 to 27 of du. So we're going to get u to the negative 2/3 from this right here, and because it's in the denominator, times du over 2. And go ahead and pull that 2 out to get us our integral of 1/2 times the integral of 1 to 27 u to the negative 2/3. So now if we go ahead and go back, we can go ahead and get, so now if we integrate this, we're going to get u to the 1/3, and then that inverse is going to be times 3. And of course we have our 1/2, so we're going to divide by 2. And then we're going to go from 1 to 27. So, and actually what we can even do right here is we can even go ahead and pull out this 3/2, and then we can just look at it from u to 1/3 from 1 to 27. So if we have 3/2 times the cube root of 27 is going to just be 3. And then, or let me go ahead and just plug it in so we can see. 27 to the 1/3 minus 1 to the 1/3. Cube root of 27 is 3. Cube root of 1 is 1. So we get 3/2 times 3 minus 1, which is 2, which brings us just to 3. All right. Since I want to try to get to some area, I don't think we'll have time to touch on symmetry, but just long story short, if f is even and you're going from negative a to a, you can actually use symmetry to break that down and say that like from negative a to a can be broken down to 2 times 0 to a. Just that way it's one less bound you have to worry about. And if it's odd, then if you're going from negative a to a, everything's going to cancel out and go to 0. So now let's go ahead and touch on area between two curves. Like if we have time at the end, I may go in more explanation and do some more examples, but we only have about 20 minutes left. So area between two curves. So what we can say, so let's say we have two curves. We have one looking like this, and we have one that goes like this. If we want to find the end, then let's say we're going to mark off our region from here to here. So the thing is, we can go ahead and if we take the area of this red region here, which let's call this f of x, and let's call the purple g. If we take the area under f of x, that's going to get us this little hatch right here. If we take the area of g of x, we're going to get this hatch down here, but granted this is all under the x-axis, so this part is going to be negative. It's going to be a negative area. But let's say we wanted to find all of this right here. So what we can say is that we have our f of a, our f of x is on top. And then we have a negative area g of x, but really what we're wanting to do is kind of add that back. So what we're going to do is technically subtract g of x, the area of g, but remember that's a negative. So that's going to get us the full area of all of this together. Now let's say that we have two functions like this. We still have an f and a g, and f looks something like this, and g looks something like this. So once again, if we take the area under f, we're going to get a nice little area right here. If we take the area under g, we're still kind of within that same little range right there. But let's say we want the area between these two curves. Well, you have that bigger area and that smaller area. So wouldn't it make sense to subtract the smaller from the bigger? So we'd have a sub f is our bigger, and subtract our smaller, and that's going to get us that area in between. So looking at that, what we can actually do in the mathematical definition says that the area A of the region bounded by y equals of x, y equals g of x equals a, and x equals b, where f and g are continuous, and f of x is greater than or equal to g of x for all x's in the interval from a to b is equal to a is equal to the integral from a to b of f of x minus g of x dx. So now let's go ahead and do an example kind of working with this. So in this example, we want to in this one, we are going to sketch the region and set up the integral to solve for the area of the region enclosed by y equals x, y equals sine of x equals pi over 2, and x equals pi. Alright, so now let's go ahead and first let's go and sketch our region. So we know that this is pretty much going to stay within our first quadrant, just kind of based on our regions right here. Or at least it's going to be on the, at least in our right half. So first let's go ahead and kind of sketch our y equals our sine of x. So we can go ahead, we know the key points for y equals sine of x are going to be 0, pi over 2, and pi. And if we kind of go up here, we have our pi over 2, and then our pi. So, and then go a little lower, we have our 1. So, of course, whenever we go up to pi over 2, we get to pi over 2, we go all the way back up to 1. Then we go down, then at pi we're back down to 0. Go under, and then, yeah, that's really all we need to worry about for right now. Y equals x is going to look a little something like this. And then, of course, we have our region set up between pi over 2 and pi. So what we're looking for is this area right here, below y equals x and above y equals sine of x. So if we're going to set up the integral, we know that our setup is going to be so we have our basic is going to be integral from a to b of f of x minus g of x dx. So if we set this up using what we have, we can say that our area, our bounds are going to be from pi over 2 to pi. And then our f of x is going to have to be our bigger function, the one that's always going to be higher, which in this case is going to be x. And then we're going to subtract by the smaller function, so sine of x dx. And we're just going to go ahead and set up, we're not going to solve it just yet. We have done a lot of integrals today in the past couple of weeks. So now sometimes they'll give you a situation to where the curves already intersect. In that case, they may not give you any intersection points. Or sometimes they'll give you bounds, but you still need your intersection points to kind of see what you're going to do with your area. Because for example, let's say they give you two functions. Because they could still give you like two functions, one's like this, one's like this, and they set your bounds from here to here. You still are going to need that to kind of figure out your areas. So let's go ahead and work on doing our intersection points. So in this one, so in this example, we are going to sketch and find the area. Or we'll actually set up the integral to find the area enclosed by y equals 12 minus x squared and y equals x squared plus 6. Alright, so first let's go ahead and set up and go ahead and sketch the graph real quick. So we know 12 minus x squared is going to start off kind of high. Let me go ahead and give that a color. There we go. And it's going to start kind of going down like that. Just like a normal parabola. And we know x squared plus 6 is going to be, once again, a parabola. It's not going to start quite as high, but this time it's going to face up. So therefore, the area that we're going to look for is going to be this spot in between here. And we can also see that our 12 minus x squared is going to be our bigger function, and our x squared minus 6 is going to be our smaller. So first now we can go ahead and start setting up our integral. So we can say our area is equal to the integral, and we know for sure that's going to be 12 minus x squared minus x squared plus 6 dx. The only thing is we don't know our bounds yet. So to solve for our bounds, what we're going to do is we're actually going to set our two functions equal to each other. So we can say that, so we have y equals 12 minus x squared is equal to y minus x squared plus 6. Now it's just a matter of solving for x, so we can get 6 is equal to 2x squared. X squared is equal to 3. So therefore, x is equal to plus or minus the square root of 3. and therefore that is going to be our integral setup. All right. And then sometimes we may have a curve to where you have several intersection points, like more than 2 intersection points, and that's when things get kind of interesting. So in this one, let's look at, in this one, let's go ahead and set up if we have time, we'll solve it, but we'll see. Sketch and set up integral to solve for area enclosed by y equals x, y equals x cubed, x, and then x equals plus and minus 1. So first of all, let's go ahead and sketch our area. Or sometimes it's not even multiple intersection points, it's just one switches from being higher to lower. It's kind of the same, but it's the same concept behind it. So if we have all right, well, okay, yeah, I was getting my head mixed up. So if we have this right here, actually, I'm going to switch colors for that. I'm going to switch colors for this x cubed function. We can see that we have an area here and an area here. We can also see that it switches between which one is bigger, right here at x equals 0. So, and really we have to worry about that because we know our intersection points are at 1. So over here we have intersection points at x equals -1, 0, and 1. What we're going to have to do is we're going to have to split this up into separate integrals. So when x is less than 0, x cubed is going to be greater than x. When x is going to be, and then over here on the right side, x is going to be greater than x cubed. So we're going to have to go ahead and split this up into 2 functions. So what we can do is we can say that a sub 1 is going to be this part right here, and that is going to go from -1 to 0 of x cubed, because that's the bigger function, minus x dx. Then we can say that a2 is equal from 0 to 1 of x minus x cubed dx. in order to take into account that. Because as we said from that last one, both of these are going to be even or both odd functions. And we know that if we're going, this kind of goes back to that symmetry. Because these are both odd, these two areas are going to be equal to each other. So therefore, if we just did, our area was equal to -1 to 1 of f minus g, that would just get us to 0. This is showing us both, like both pieces that we're going to need to actually solve this. So then from here, what we can do is we can say this whole area is going to be equal to A1 plus A2. And so that's essentially your strategy, is if you have several intersection points or just several little sections of area that you have to find, you have to give each one its own integral. Otherwise, you're going to kind of start chopping off pieces or things are going to get jumbled. So you're going to have to always split that up into different pieces. And that is all we have time for tonight. So I believe we're trying to figure out an exam review, a final exam review. We'll see if we can get that going. So maybe try to keep an eye out for that. But other than that, have a wonderful evening.